My name is Aurora Micheli. I'm a PhD student at TU Delft in the Netherlands. And today I will present the paper Deep Activity Propagation via Weight Initialization in Spiky Neural Networks. So as the title already suggests, the question we try to answer here is, what is a good weight initialization for a spiking network? And we think this is a relevant question because we know from literature that if we choose a poor weight initialization, we might run into, for instance, exploding or vanishing activations in our network. We can have issues with the gradients, and we can definitely have a hard time when we try to train a network. While if we pick a good weight initialization, then we're happy because in principle we can avoid all these problems. And our work starts from the observation that very often spiky neural networks are initialized following standard strategies that were initially derived and designed for conventional networks, so ANNs. And these strategies are tailored to a specific activation function. So for instance, we have the Xavier initialization method for the sigmoid, and we have chiming for the ReLU activation function. However, as we all know here, spiking networks and conventional networks are intrinsically different, right? So in spiking networks, we have a different neuronal dynamics, we have spikes, and the activation function itself is different. Therefore, the point we want to make here is that ANN initialization schemes can be inadequate for spiking networks. And we do so by, first of all, analytically deriving a weight initialization method that is specifically tailored for spiking networks and for their activation function. We then validate on simulations that this method indeed can ensure stable spike propagation, which means that we can avoid the dissipation and the amplification of spikes. And lastly, we show that having a good weight initialization can also help when we have to train a network. So we can speed up the training and we can also get a better performance. So let's have a look at the proposed method, first of all. We consider the feed-forward fully connected SNN initialized at time 0. And so for a generic layer L, we can write that the neuron's membrane potential, so UL, is equal to the weights of the layer, so this WL times the input spikes, XL. And then XL is computed by applying the activation function to the membrane potentials of the previous layer, so this UL minus 1. And the activation function, of course, here is the Heaviside step function. Now, our derivation follows the approach that was proposed by Kai-Ming He in this paper, and that led to the well-known and broadly used Kai-Ming initialization for ANNs. And this approach suggests that a good initialization method should avoid reducing or amplifying the magnitudes of the input signals. How? By keeping the variance of the input to each layer constant. So since this Wx is the input to our layer, we can take this first equation, we compute the variance on both sides, and we want this quantity to be constant across layers. Now we can just rewrite the second term by assuming that the weights, so W and X, are independent of each other. And we end up with this equation. Now, up to this point, actually, the derivation is exactly the same. It's identical to the one you find in Kai-Ming's paper. But here is where things become a bit more interesting because we remember that this XL is computed by applying the activation function to UL minus 1. And if we assume the same pre-activation distribution, so the distribution of this UL minus 1, we see that depending on the activation function we use, the post-activation distribution, so the distribution of XL, changes a lot. So you see here in the top row, we have the ReLU, and this is the distribution we get. But if we use the Heaviside function, then the distribution is completely different. Therefore, we also expect to find a different result for the weights. And okay, you can find the details in the paper for the sake of time, but the main idea is that by considering the specific activation function of a spiking network, we can get, and okay, by enforcing the conservation of this variance, we can derive what the optimal variance for the weights should look like. And what is interesting to notice is that if we assume the firing thresholds of theta to be greater than 0, which is, well, almost always the case, and okay, the distribution of UL minus 1 to be 0-centered, then we find that the variance for a spiking network needs to be strictly greater than the variance for NANN. Okay, then we empirically validated these findings. So we used a fully connected SNN with leaf neurons and with 100 layers. And here the input is drawn from a standard Gaussian distribution. So we compute the variance of the UL across layers for different values of the firing threshold. And then we compare our initialization with Keiming's one. And what we find is that indeed, with the proposed method, unlike Keiming, we are able to keep this variance constant across layers, which is nice because it's exactly what the theory predicts. We then also compare this method with other baselines. And again, what we find is that only our method and partially method 15 are able to, again, keep the variance constant. And as a result, we see that also the spike count then becomes constant, which is nice because we want to conserve spikes from the input to the output of our network. Okay, so far I only mentioned networks initialized at time 0, but we know that spiking neurons, they integrate information over time, right? So we repeated the same simulation using multiple time steps. So in this case, we have 20 time steps. And what we see is that while our method doesn't explicitly account for time, it is still able to approximately conserve variance and spike count. So here you see on the left, so the left column is our method, again, for the as a proof of concept compared to Keiming. And you see that in the case of Keiming, everything dies out, goes to 0. Okay, lastly, we also tested this method on 4 different image classification datasets using both fully connected networks and convolutional networks trained with backpropagation. And again, we consider 7 other baselines, both for ANNs and SNNs. And what we found is that while all the methods perform pretty well, if we use the MLP on neuromorphic MNIST and the CNN on fashion MNIST, possibly due to the simplicity of the task. Only our method and 15 seem to be effective if we train the MLP on MNIST and the MLP on fashion MNIST, while for the CNN on CIFAR10, we see that indeed this method can improve the classification accuracy. So to wrap up, what we did in this paper, as I mentioned, we derived this new variance conserving weight initialization, specifically tailored to the activation function of a spiking network. And we validated that indeed, using this method, we are able to preserve the spikes from the input to the output. And then we also show the effectiveness of using a proper weight initialization when we train a network. Then there are also some limitations, of course. So first of all, as I said, our method doesn't take time into account. So we're not really solving for the temporal dynamics of the neurons. So I think it would be very interesting to extend the theory. And of course, also validate this effectiveness on more complex architectures and datasets. And with this, I thank you for your attention, and I'm happy to receive any questions.